Okay, hi grade 10s. We're now going to move into our next topic on refraction, which has something to do with refraction and reflection. It's called total internal reflection. And again, Bill and I talked about this. He showed you had a big tank of water that had some green food coloring in it, or maybe he was using a green laser. I can't quite remember. But he showed you if you shine light through the water in the fish tank, it will actually at some point reflect back inside. So we're looking at refracting or bending the light so much that it actually then reflects in the substance that it was in. Okay, so I want you to look at this little video here. This physics teacher set this up for me, so I'm going to use this one. All right, and you're going to see the incident ray coming from a ray box through a plastic or an acrylic box. So you can see that box there. Can you see where the normal is on that diagram? Okay, and can you see the refracted ray? So the incident ray going into the acrylic block, and then can you see the ray coming out? And can you see there even that it's speeding up as that refracted ray comes out of the acrylic block? And I could measure that, right? On that diagram, could you measure the angle of incidence, the angle of refraction, and can you see that as light speeds up, as it changes in the second medium, it bends away from the normal. So I could actually put well, you can see he's got some measurements on there for the protractor, and you can actually do that measurement. You can calculate those angles. Now I want you to see what happens as the light bends so much. So we're going to just watch the video as it plays through, and you can see at some point that the light gets bent, continues to bend, continues to bend. It's going to bend so much that it's actually going to turn into the rainbow. You're going to be seeing, can you see at that point right there? You've got a rainbow of colors, okay? And you can see that it's bending so much, it's spreading that light apart. When that light, I'm just going to pause for a second there. When that incident ray actually bends so much that now it's 90 degrees from the normal, boom, at that point, you get the light ray reflected back inside. And you can see on that diagram, it goes up and then the light reflects back inside. The angle at which that light beam does that is called the critical angle. Okay, so let's go back just for one more second here. It's bending, 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 and then boom. Once it reaches that critical angle and reflects back in, anything beyond there will stay reflected back in as total internal reflection. And the angle at which that substance does that is called the critical angle. That's going to be unique to that substance. So every different substance or medium that the light can travel through is going to have a different critical angle. Does that make sense? It should. Yeah. So we could figure out in the lab what the critical angle is for acrylic. And then you can just see as the light continues to bend, or if he continues to move it even further past the critical angle, every single light ray will be reflected back inside, and that is called total internal reflection. Okay, I'll post this video along with the lesson so you can watch it, you can pause it, slow it down, and you can see the rainbow again. In the lab, we could do this as well, just like these done on this sheet right here. And then this note is what would have happened in the lab if we could have done that. So can you see how I've got the normal written down? I would have taken a acrylic block and put it on our piece of paper, just like so. You see that sort of semi-moon shape that we've got. And then you can see that I was going to take that blue ray here as an incident ray, shine it in, and then I started bending, 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 bending until, boom, it reached that 90 degrees from that refracted ray. So that was the blue ray going in. Once it reached 90 degrees, that's the point that's the critical angle. Okay, so between the normal and the incident ray, this angle right here is what we call the critical angle. And can you read how many degrees that is? 10, 20, 30, 40 degrees. Okay, so I can fill that in on my sheet even though we didn't do the lab. What is the angle at which that takes place? And it is 40 degrees. And for this substance, that is the critical angle. The second part of this lab activity is just to take then, all right, we'll continue the ray box and make another incident ray and measure and see what happens to the refracted ray. And you can see right here, you've got your incident ray 2 going in, and then you've got your ray coming out. And in fact, that is now a reflected ray. Why? Because it was reflected back into the medium. Okay, all right, there's a summary on the back, and I'm just going to talk our way through that fairly quickly, and you can fill it in and see if you get the same, if this makes sense. All right, so here I've got an incident ray going in. You can see my water down below. Of course, it's an incident ray because it's, do I need to write that on the sheet? Incident ray, okay? You've got your refracted ray, and if you've got a light beam shining from water to air, it's going to speed up. If it speeds up, it's going to be bending away from the normal. Again, could we calculate the exact angle? We sure could. Are we going to do that this year? Not really, okay? But you know that it speeds away because it's less, speeds up because it's less dense, and in fact, the index of refraction for air and water, 1.0 and 1.33. Okay, then we reach the critical angle. So we bend that incident ray even further. And as soon as the refracted ray reaches that 90 degrees, that's the critical angle. If this substance is water, we know that the critical angle can be calculated, and it's actually 48.8 degrees. So the angle of incidence is equal to the critical angle when it reaches that 90 degrees for the refracted ray. And then as you move that incident ray beyond the critical angle, it reflects back in, and the angle of incidence again would be equal to the angle of reflection. Does that make sense? Okay, that this angle right here is equal to this angle right here, and that obeys the law of reflection again, doesn't it? Okay, all right, so there are a few questions here for total internal reflection. This is the concept that makes our fiber optic cables work, and there's some really cool maps you can look at online to see all of the fiber optic cables that essentially run our internet. How does the internet go from here to the other side of the world? Total internal reflection. Okay, all right, so good luck with that. Let me know how it goes.